It's time, no? What happened?
Ma'am, I think the participants are yet to join. Once a few more join, we can start, I think.
Okay.
Ma'am, hello.
Chitra madam?
Can we start, ma'am?
Yes, you can.
Yes, ma'am. Okay. A happy afternoon, everyone. I welcome you all to the second day of our EC webinar series. We are gearing up for an interesting topic today in this hot afternoon. What do you want to do with your own gold? Hosted by Department of ECE, Savita Engineering College. As our model research associate, University of Exeter. Ma'am, please.
Thank you, Chitra. Impressions is the webinar series by our alumni of EC Department and Savita Engineering College Alumni Association. Savita Engineering College alumni அனைவருமே முத்திரை பதித்தவர்கள் என்ற கருத்தை பதிவு செய்வதே எங்களது எண்ணம். Dr. Ritvik Reddy Gutta, a Savita Engineering College graduate, earned his bachelor's in Electronics and Communication Engineering in 2014. It was at Savita he was first introduced to micro and nanotechnology by his advisor, Dr. S. Praveen Kumar, professor of EC department. He later earned his doctorate in optical science and engineering with nanophotonics as major from the University of Alabama in Huntsville in 2019. He was advised by Professor Syed M. Sadagi, a pioneer in the field of exciton plasmon coupling technology, for his PhD. While at University of Alabama, Ritvik was awarded the Outstanding Graduate Researcher for 2018 by the College of Science. He currently works as a postdoctoral research associate in Professor Frank Walmer Laboratory of Nanophotonics and Biosensing. His current research interests include developing whispering gallery mode sensors and spectrometers. Ritvik has published 33 peer-reviewed journal articles so far and has given various talks in international conferences. We are glad to have Dr. Ritvik with us today for the first session of Impression.
Thank you, ma'am. I now request Dr. Ritwik to take over the session.
Thank you, Padma Priya ma'am, and thank you, Chitra ma'am.
Yes, sir.
I'll start sharing my screen.
Yes,
Just
sir,
let me know
sure.
if it works. Yeah.
Yes, sir, sure. Yes, sir, it's working fine.
Okay. Yeah.
You can start your presentation.
Okay. Good afternoon, all the staff and students who are attending this webinar today. I'd like to talk about what I've been doing with gold nanoparticles for the past 6 years now since I graduated from Savita Engineering College. So the title of my topic is, what do you want to do with your gold? So when we think about gold, what do we first think of? We do often think about gold blocks, which a lot of international banks and Reserve Bank of India and all the big banks usually store them as. And also when you think about gold, you think about jewelry. A lot of people also, especially in India, we spend a lot of money on buying gold and making jewelry out of them. And also some rich families might also have even gold utensils at their home. But let me give you a few more choices of what you can do with gold. What do you think these are? Well, let me tell you, these are gold nanoparticles dissolved in water. And as you can see, gold nanoparticles don't look like solid gold anymore. Well, you can see yellow gold here, but also you can see different colors of gold also here. Now, why does these gold nanoparticles look a lot different from bulk gold or a gold block or gold jewelry or gold utensils? Uh, so let's see what is the physics behind why gold nanoparticles look different from the regular gold we see in everyday life. So first, let's talk about gold, a sheet of gold. So if you look at a sheet of gold, it obviously looks yellow. Why does it look yellow? Because when you incident light on a sheet of gold, it absorbs blue light and it reflects black. It reflects back the other two major light wavelengths, which are red and green. And the mixture of red and green is yellow. So your eyes see yellow color. Okay. At the same time, what happens when you incite a sheet of gold with light is that obviously gold is a metal, so it has a lot of free electrons on top of it, right? On the surface of the gold, right? So when you excite these free electrons with a light source, which consists of photons, these free electrons start oscillating, they start vibrating. And vibrating electrons, what do they cause? They cause electromagnetic field. So let me play this video. So you see, you have a sheet of gold and you excite it with a light source, and you have these free electrons which vibrate, which causes an electromagnetic field. This electromagnetic field is a traveling wave. Uh, you might have heard about standing wave and traveling waves as part of your physics courses. So the electromagnetic field which is generated on this gold sheet is a traveling wave. Now, what happens when you use gold nanoparticle? When I say gold nanoparticle, the nanoparticles I'm talking about are of the size of few hundreds of nanometers. The size which is compared to the light wavelengths which we can see, the visible light wavelengths, which are from 400 nanometers to about 750 nanometers. So if you make a gold nanoparticle, which has a size within the range of 400 nanometers to 700 nanometers, what happens when you hit it with light? Since the light wavelength is similar to the size of the nanoparticle also has free electrons because it is also made of gold. So the free electrons on the gold nanoparticle start vibrating. And again, these vibrating electrons create electromagnetic field around this nanoparticle. But since this is a nanoparticle and not a flat sheet, what happens is the electromagnetic field created is not traveling anymore. Rather, it is a standing wave, which means that the electromagnetic field is highly concentrated around this nanoparticle alone. So you have a huge concentration of electromagnetic field around this nanoparticle. Another important feature you have to consider is when you have gold nanoparticle, there is a lot less light reflected back when you compare to a sheet of gold, and also a lot more light which is transmitted from the sides and around the nanoparticle, which again does not happen in a sheet of gold. So you have a lot more light just passing through and a lot less light reflected back, and there is a huge scattering of light from the gold nanoparticle. This scattering of light, let me explain it in simple terms why this scattering of light happens in a different way compared to a sheet of gold. So you have these free electrons, right? When these free electrons oscillate, obviously they generate electromagnetic field, but these free electrons cannot keep oscillating. They have to come back to a ground state. And how do they come back to a ground state? By generating a photon with the excess energy they have. And the energy of the photon which is generated out is what the color of the nanoparticle you see in all of these bottles. So depending on the size of the nanoparticle, you have different number of free electrons which oscillate at different wavelengths, and they generate out photons at different more wavelengths. So if you have a smaller nanoparticle closer to the range of 200 or 300 nanometers, you might see it in the blue wavelength range. But if you take a slightly bigger nanoparticle, let's say the nanoparticle is around 800 nanometers, the light which is scattered from the nanoparticle might be around 700, 750 nanometers, which is the red wavelength. That's why, depending on the size of the nanoparticle, the wavelength of the light which is scattered from the nanoparticle changes heavily. So you can just tune the size of the nanoparticle and generate different colored solutions. And another important thing which I'd like to mention here is, obviously, when these electrons want to relax, they give out the excess energy through photons, but not all electrons release photons to relax. Some of the electrons also dissipate their energy via heat dissipation. So also the nanoparticle is quite hot when you excite it with photons or light. So two things happening here. When you in when you hit this nanoparticle with light, it absorbs some light, transmits more of the light, and it scatters a bit of light. At the same time, it also makes the nanoparticle very hot. Now we use these properties of making the nanoparticle very hot and scattering of the light at different wavelengths for sensing applications. From here on, uh, I'll talk about how I use this technology for biosensing, and also for detection of various chemicals in a given solution. And also I'll talk about few more applications of how you can use these gold nanoparticles in other important technologies. So the phenomenon of free electrons on gold nanoparticle, when they vibrate, they generate the electromagnetic field, is called localized surface plasmon resonance. The definition is clearly here. When you have a metallic nanoparticle, you excite it with a light source, the free electrons on them, they absorb some of the light source, and then they generate electromagnetic field because of the oscillating of these free electrons. And the LSPR depends on the shape and size of the metallic nanoparticle, and also the refractive index in which these nanoparticles are placed in. By that, what I mean is, if you place this metallic nanoparticle inside water, it behaves differently when you put this metallic nanoparticle in another liquid, let's say in a juice or in an alcohol. For example, I show you here an absorption spectra. This is an absorption spectra which shows at what wavelengths this nanoparticle absorb light. So if I hit a single nanoparticle with a broadband source, by that what I mean is all of the visible light wavelengths from 400 to 700 nanometers. If you have a spherical nanoparticle, it absorbs a single wavelength or in the wavelengths of from 400 to 550. But if I change the shape of this nanoparticle to, let's say, a pentagon, it absorbs from 450 to 600. Now I change the shape of this nanoparticle to a triangle, it absorbs in a completely different wavelength, right? This is another slide which shows how the shape of the nanoparticle decides at what wavelengths it absorbs, or also at what wavelengths it scatters light. For example, here, if you have a gold nano shell, it absorbs the wavelengths from around 650 to in the near infrared wavelengths of 1000 nanometers or something like that. If I change the metal to silver, it absorbs in different wavelengths again. I have silver nanocube here, which absorbs from 500 to 600. silver nano plates, which absorb again from around 650 to 1000. So depending on shape and metal and size of the nanoparticle, it absorbs at different wavelengths and also scatters the light at different wavelengths. So you can see different colors coming from gold nanoparticles, which are of different shapes and size. Now, some of the applications of gold nanoparticles are only important ones are mentioned here, but you have many more applications of the gold nanoparticles. The application which I work on is biosensors, but there are also other important applications of diagnostics, drug targeting, pathogen detection, and also controlled drug delivery. I'll talk about my research topic, which is biosensor, and also have one slide each on the few important more applications of drug delivery and drug targeting and pathogen detection in the later part of my presentation. So one would think this technology is quite recent, maybe in the 20th, was developed in the 20th century, or maybe in the 19th century. But let me tell you what, this technology was actually first used, or at least we have proof that this technology was actually first used by Romans in the 3rd century. What they did was they used these gold nanoparticles in making this cup. Now this cup, it's called Lycurgus Cup. It is presently displayed in the British Museum here in London. What happens is when you have a light source inside this cup, and when you look at this cup from outside, it looks quite differently compared to when you have a light source outside the cup and again you look from outside. I have a short video in the next slide which actually shows how gold nanoparticles make this cup look in different colors or in a cool way. Let's see if we can play this video. Okay, yeah, here it is. As I said, it's the Lycurgus Cup. It was a luxury item held by the rich people during Roman Empire. The glass is infused with metallic nanoparticles. And the experiment here is there is a light inside the cup and there is also a ceiling light outside. So the light inside the cup is on right now. And if you're looking from outside, the cup looks pinkish red in color. And now you turn the light inside the cup off and then the ceiling light is on. And when you look from outside, the cup looks greenish. And you turn the ceiling light off again and turn the light inside the cup on. And again, the cup looks pinkish. When you're looking from the top, it looks much cooler when you're looking from the top. So first what's happening is you have the light inside the cup. And if you're looking inside the cup, it looks greenish and outside it looks pinkish. And you turn the light inside the cup off and you just have a ceiling light on. And if you're looking outside, it looks greenish, the color changes. So this was the first known proof of nanoparticles being used in everyday life. And since then, these nanoparticles have been used in a lot of Western churches where they include these nanoparticles in the glass, they stain them. And then if you go to any old church from the 10th or 9th century in any of the European countries, you see these cool glass where Jesus or even other Christian gods are shown in beautiful colors. This is not using paint. This is just using gold nanoparticles of different size and shapes. And you have these amazing images of Christian gods on these churches. And since then, they've been used in a lot of other applications too. But from now on, I'll talk about how I used gold nanoparticles in my PhD research. So as Padma Priya ma'am talked in the introduction, I did my PhD in University of Alabama, located in Huntsville, the city of Huntsville. The campus is a very beautiful campus, as you can see. And they had an optical science engineering department, which is shown here with a tiny telescope on top of the building. This university was initially set up by NASA. We have a small NASA location in Huntsville itself, which is seen here again from the university itself. There are a few rockets which you can see from anywhere in Huntsville. And to support their research and staff, they developed a university so that people who they can train students on whatever technology they want, and then they can directly hire into NASA and then make use of their talents. So at UAH, what I did was I made my own nanoparticles. So the nanoparticles which you have seen so far were colloidal nanoparticles. What that means is these are nanoparticles freely moving around in a liquid solution. But for my research, I didn't want to use a colloidal nanoparticle. So what I wanted to do was I want to use my nanoparticles on a solid surface so that they don't move around and the properties don't change. Because if I'm moving around or I tested my sample today and come back and test my sample today, and it doesn't look a lot different because the gold nanoparticles didn't come and settle down at the bottom of the glass bottle or something like that. So how do I make my own gold nanoparticle samples? I use these cover slips. These are microscope cover slips. They are made of glass. They're completely transparent in the visible range, and I do all of my experiments in the visible range. So these are perfect base for my nanoparticles. So I use one of these cover slips, which is shown here, and then I coat it with a photoresist. Now, photoresist is a chemical which solidifies when you expose it to white light. But then again, you can change the properties of this photoresist by hitting the photoresist with a high electron beam. So what we do is we have an EB lithography machine at UH, and what you do is you focus these electrons onto small spots on this photoresist and change the property of this photoresist at certain spots, right? And when you change the property, there is a certain chemical in which when you dip this sample, wherever you hit with the electrons, the photoresist is gone from those spots. So you see these missing spots of photoresist on the sample. And now we take this sample and cover it in gold. How do we do this? You heat the gold and make it evaporate, and then you hold this sample on top of this evaporated gold. So all of the gold just comes and settles on top of this sample. You can see all of the gold in here. And then finally, there is another chemical which you use to completely remove the photoresist, not just the photoresist which was hit by electron beam, but all of the photoresist which you put on the sample. And when you take off the photoresist, all of the gold on top of the photoresist also goes off. But the gold where there is no photoresist stays back on the sample. So you have these gold nanoparticles on top of this sample. This is the side view of the sample, which looks like this. But if you look from the top, you have hundreds of these on a given cover slip. And I use this fabrication technology to write a few hundreds of these samples as part of my PhD research. As you can see, I wrote nanoparticles ranging from very small nanorods to medium-sized nanorods to longest ones. The smallest ones are 200 nanometers in size, and the longest ones here are about 1200 nanometers in size. I've also written some moon-shaped nanoparticles, arrow nanoparticles, bow tie nano antennas, head shaped, and even plus shaped. I wrote few more different shapes, which I didn't show in this presentation. But yeah, we use all of these samples for biosensing. And in the next few slides, I'll talk about how we use these samples for biosensing. Uh, Another important thing I'd like to mention here is the concentration of the nanoparticles matter. By that, what I mean is, okay, yeah. Okay, yeah. The concentration of the nanoparticle, I guess I missed one slide here. Okay, let me go through this slide. So what we do with these nanoparticle samples is we do absorption measurements on them. That is to find out at what wavelengths or at what wavelength of light does this sample absorb light. So for example, here I show this nanoparticle sample, which has 200 by 100 nanoparticles on it. And what we do is we place this sample just after a microscope objective through which we send broadband light source, which is again, you have a visible light source range having wavelengths from 400 to about 700, and we'll collect the light behind the sample. So you send light from one side of it and collect the light on the back side of it and send it through a spectrometer. And now what this cool spectrometer does it collects the light, and then so the light which is coming back on the other side is a transmitted light. So it takes a transmitted light and does inverse of it. So what you get is the absorption of light. And this is how the spectra looks like. So for this sample, you have a lot of absorption at around 800 nanometers. And also you have a little absorption around 600 to 700 nanometers. Now, if you change this sample into another sample which has a different shape or size of nanoparticle, the spectra looks completely different. Okay. And okay, now let's talk about the number of nanoparticles. The number of nanoparticles and the sample matters a lot. Now, why I say that is, let me go back one slide back. So here, if I don't have these many nanoparticles, let's say if I have 1 or 2 nanoparticles here, you have very less amount of light being absorbed, which shows up at a slight bump in your spectra. Whereas if you increase the concentration of nanoparticles, here it shows all these colors are related to the concentration of a nanoparticle in a given solution or a given size. The peak, the intensity of the peak increases, which is the amount of the absorption by the nanoparticles increases. And for all of the experiments, it is really beneficial to have a nice strong peak so that you can track this peak, how it moves when you change its properties. I'll tell you what properties those are. Okay. This is another important feature. What this slide shows is when you have two samples. In one sample, I have nanoparticles placed far away from each other, and I record its absorption spectra. This is how it looks because you have the LSPR or the absorption happening only from one nanoparticle. But when I put these nanoparticles very close to each other, what happens is the LSPR or the scattered light from this nanoparticle starts interacting with the scattering light of the immediately next nanoparticles, both this one and this one. And you have a lot of more complicated optical phenomena happening. So you have a completely different looking absorption spectra. Now, when you compare both of these absorption spectra, you can see there is a lot more absorption spectra. If you see on the y-axis, you have an absorption of around 0.7, whereas if you see here on the y-axis, you have an absorption of 0.07. So it is almost 10 times more strong. And also the wavelength at which it absorbs changes. Here it's around 1450, whereas here it's around 1000 nanometers. So you can change the absorption properties of these nanoparticles by spacing them at different distances from each other. And you tailor the properties in whichever way you want. You want strong absorption or you want absorption in 400 to 500 nanometers range, or you want absorption in near infrared, which is from 750 to 1500 nanometers range, which is around this wavelength range. You can tailor it however you want just by spacing the nanoparticles at different distances. Okay, now how do we use these devices for sensing? Let's go back to the image which I showed you to discuss what LSPR is. So you have a nanoparticle, you excite it with light. What happens again? The free electrons on this nanoparticle starts vibrating or oscillating, and to relax, they scatter some light from it, which is the same case here. You have a nanoparticle on a glass slide surrounded by air. You excite with light, it scatters light at different wavelengths, right? But what happens when you cover this nanoparticle with water, like in this case here? Does the free electron still vibrate or oscillate at the same frequency as they do when it is surrounded by air? No, it does not. So the vibration or the oscillation frequency changes because the refractive index around this nanoparticle is different now, which is the refractive index when air was surrounded by the nanoparticle was 1. Now, when you surround the nanoparticle with water, the refractive index changes to 1.33. And light obviously behaves different when you have different refractive indices, right? That's what Snell's law teaches us. And here, as an example, I show you the absorption spectra. When you have a nanoparticle surrounded by air, you have this, the absorption spectra looks like this. But when you cover the nanoparticle with water, which is the red line here, it moves or it shifts from 550 to about 650 nanometers. So there is a 100 nanometer red shift. We call this red shift because the peak is moving towards the red wavelengths, the higher wavelengths. And what if I take this water off and put another water solution which has a concentration of glucose next to it? You see there is a little more redshift happening, maybe 10 nanometers or 20 nanometers. Now this amount of redshift depends on the concentration of glucose you put in water. If you use a lot of higher concentrations in water, the redshift might be a lot more because you are increasing the refractive index by mixing glucose inside water. Now the refractive index of water is not 1.33 anymore. It is somewhere in between the refractive index of water and the refractive index of glucose. To be frank, I don't know what the refractive index of glucose is, but it's definitely higher than the refractive index of water. And now what happens when you completely take water off this nanoparticle and put ethylene glycol around it? Now ethylene glycol has much higher refractive index, which is close to around 1.38, around 1.4. You see a little more redshift in the peak. So the absorption peak keeps moving to the higher wavelengths when you increase the refractive index around this nanoparticle. This is a simple optical property which we use to use these devices for biosensing. Now, in this slide, we show you these are the experiments which we did in our lab. What we did is we used a device which had nanoparticles as shown in here. Each of these nanoparticles is around 200 nanometers by 100 nanometers, and each nanoparticle is separated from another one by 500 nanometers by 500 nanometers, both along x and y axis. So what we did is we took this device and we recorded its absorption spectra, and this absorption spectra looks like this, the blue line. And after that, we took this device and did some bioconjugation to it. By that, what it means is, since it is gold nanoparticles, the gold molecules have very high affinity to certain biomolecules, which you can find in all living organisms. For example, streptavidin, it is a protein which you can find in all living cells on this planet. And it is very important to detect this streptavidin in a given sample solution to see how much of this protein is there in a human body, because lack of it might create some disturbances inside human and cause some diseases. So what we did is we used some uh, chemicals to combine or to put this streptavidin on each of these nanoparticles, and we did it in a such a way that there is no more than one streptavidin protein attached to a single gold molecule. What you call this is a monolayer conjugation of streptavidin to gold nanoparticle. Now, if you look at the whole length of this, this is about 10 nanometers, which is not big compared to especially the nanoparticles. 10 nanometers is like 2 times the size of a given protein and 100 times smaller than a virus. Let's talk about COVID virus, since that's the hot topic right now. COVID virus is about 100 to 200 nanometers long. So it's these streptavidin is almost 10 times smaller than COVID virus. So after we conjugated this streptavidin to this nanoparticle, we did the same absorption measurement again. And then when we did the absorption measurement, we saw changes in this absorption spectroscopy. Now the peak doesn't lie in the 720 to 730 nanometer range anymore. It redshifts to around 750 nanometers. And just by having a monolayer of this streptavidin, and if you can detect or if you can see 20 nanometers of redshift in your absorption spectroscopy, it is a very high improvement in sensing technology. And this was published in Nanotechnology Journal. And I also got to present this at SPI Photonics Fest in San Francisco. Okay, so this was a part of my PhD research topic. Now, after I graduated from UAH, currently I'm working as a postdoctoral research associate in Frank Walmer's lab. What we do in our current lab is we use much more sensitive sensors, even 1,000 times sensitive than what I've shown you so far. And I wanted to use all of my knowledge, which I gained as part of my PhD, and apply it in the technology which he uses in this lab. So I'm going to talk to you about what he uses in his, what kind of technology he uses in his lab in the coming few slides. So this is the University of Exeter, where the Walmer lab is currently working at. It is, again, very beautiful campus located in the city of Exeter. Actually voted as the most beautiful campus in UK in 2015 or 2016. But yeah, here there is a small building called Living System Institute, where physics, biology, and chemistry come together to solve real life issues like cancer treatment or devising very sensitive sensors. For example, virus detections or DNA detections, or to check how DNAs evolve if you put them in different chemicals, or how to create drugs and track these drugs in human body. Well, they don't do directly on human body. They initially start with rats or some other animals, and then they give it to a government organization to continue with the research. But yeah, that's what they do in this Living System Institute. But what the Walmer group actually does is they work on a specific technology called whispering gallery mode technology. I'll explain to you what this whispering gallery mode technology is. So this is St. Paul's Cathedral. It's a big cathedral, Christian cathedral located in London again. There might be other cooler reasons to visit this cathedral, but the most important reason I would visit this cathedral is, on top of this cathedral, there is a dome. And in this dome, there is a walkway, as you can see on the edges of it. right? On the edges of it, you can walk around, and the walls around this walkway are so smooth that if a person stands on the other side of this walkway and whispers into the wall, you can stand on this side and hear what is whispering into the wall. You can see visitors trying to listen to whatever the other guy whispered into the wall on the other side of the walkway here. Now, why does this happen? It happens because the acoustic waves, which are the sound waves we talk when a person talks, they keep internally reflecting around this walkway, and they travel around this walkway so many times, and it amplifies so that if a person even standing on the other side of it few meters away from the whisperer, you can still hear it. And this is an important technology because you cannot usually hear a person who is whispering to himself even if you're standing like 2 or 3 meters away from him. But in this case, if you can stand literally about let's say 50 meters away from a person who is whispering, and you can still hear what is talking actually very clearly. Few of my lab members actually went there and they tested it out, and yeah, I'm looking forward to visit it too and test it out myself to see how good it actually works. But the important thing here is you can use the same technology not just for acoustic waves, you can use them for optical waves too, using the principle total internal reflection, which you're all familiar with. You have probably learned about it in your physics class. What happens in total internal reflection? Again, you have two refractive indices media, and if we send light from a lower refractive index to a higher refractive index material at critical angle, you mostly hear about this in fiber optics. You trap the lights inside the fiber optics, and the light keeps traveling in the fiber to the other end of it. You can use the same principle. Send a light into, you usually call these resonators because it resonates at, it traps a light inside it. You can trap a light inside it, send light into it, and then the light keeps reflecting totally internally, and since it's a circular object, the light is just stuck inside it, traveling around, round, round. And scientists say usually once you send light into it, the light goes around this resonator a couple of thousands of times. Okay, but the only difference between this acoustic whispering gallery mode and optical whispering gallery mode is the size at which you use them. As you can see, the acoustic whispering gallery mode, you need a huge pathway, about few tens of meters of length, to make this possible. But in optical whispering gallery mode, again, you need to have the resonator comparable to the size of the optical wavelengths, which are hundreds of nanometers or 1 micron, a few microns. Okay. Now, how do you trap light inside it? Forget about this tapered fiber written over here, but what you can do is you take this micro resonator. We call it micro because these resonators are usually 1 to around 100 microns of size. So you call it as micro resonator. And you send light tangentially very close to this resonator. You leave, let's say, maybe about 100 nanometers of gap in between the light and the resonator itself. And when the light is going tangentially, you have some evanescent field, which means the outside edges of the light naturally gets trapped in this resonator, which means it somehow enters this resonator and then it gets trapped because of the total internal reflection property of it. And if you record the light on the output side of it, what happens is you see a spectrum which looks like this. What this spectrum is, a transmission spectrum, because you're just transmitting the light. Some of the light is missing because it is trapped inside the resonator. The light which is missing is showing up as this dip in the spectra. And if you remember the spectra which I showed as part of my PhD, they look quite broad, and also the peak went up because that was absorption spectroscopy. This is comparatively a transmission spectroscopy. So they're just inverse of it. You do one minus of the other, you do one minus of absorption, you get the transmission. That's it. But the important thing to compare is the peak here is very sharp compared to the peaks which I've shown you. I don't know if you can see the wavelength range on the x-axis here, but it is few picometers wide compared to the few hundred nanometers which you saw the research which I showed as part of my PhD. This is such sharp because you're trapping only certain wavelengths of light inside this micro resonator. And the wavelengths which you can trap are based on the size of the micro resonator itself. So if you change the size of the micro resonator from 1 micrometer to 2 micrometers, instead of absorbing at 640 nanometers, it absorbs at 680 nanometers. So it depends on the size of the micro resonator. Okay, are we all clear with this? Next, what I'm going to show is the different kinds of micro resonators which scientists or researchers have developed so far in the past, let's say 30, 40 years. This technology is quite new in the optics, actually. In the acoustic waves, it's quite old. The cathedral was built about 300 or 400 years back. So the acoustic technology is quite old, but the optical technology is about 30 or 40 years old. That's it. And in the past 30 or 40 years, the scientists have developed different kinds of resonators with different shapes. The most common one is a microsphere. It's easy to make. You can use a glass bead or a fiber and heat it with a CO2 laser. CO2 laser is very strong or has very high power. So you burn it and you have these small balls which fall down. You collect them and you have a microsphere. You also have micro cylinders and you have micro discs. This is also micro disc, micro ring, micro bubble, and a micro capillary. Now, one major requirement for light to be trapped in these micro resonators is the surface should be really smooth, because if you have any small bumps or non-uniformity in its shape, the light which is trapped inside will start escaping slowly. So eventually, after few femtoseconds or picoseconds or nanoseconds, the lights start dissipating. So you lose the technology, you lose the important properties of this technology if you have a rough surface. So it's really important to make this as smooth as possible. Now, how do we use this technology, the whispering gallery mode technology, in our lab? Is we take this microsphere, we change the pH of this microsphere by dipping it in a very diluted acid or a base. By doing that, you change the pH of this microsphere, either reduce it below 7 or higher than 7. And then gold apparently stick to any material which has lower pH, or it could be the other way, the higher pH. So once you change the pH of this microsphere, the gold goes and sticks to the microsphere. These are gold nanoparticles. So you put these gold nanoparticles in water, mix them well, and then you dip this microsphere inside this solution and leave it there for a few minutes, and you have all of these nanoparticles inside the solution which come and stick to this microsphere, right? And then if you're trapping light around it, the light now has to go over the gold nanoparticles, right? Obviously, you've seen in previous slides, when light hits gold nanoparticle, you have the plasmon, which is the vibration of the electrons happening, and then you have higher electromagnetic field around this nanoparticle. So you have higher sensitivity. So we combined the plasmonic properties of the nanoparticle with the optical properties of the micro resonator here. So put together, they are called Opto-Plasmonic devices. I don't know how to get rid of this, but that's fine. Okay, it's called Opto-Plasmonic devices, a sensor devices. And now how we use this Opto-Plasmonic sensor devices is we try to detect single ion, molecule, protein, or virus. Now, remember, we are talking about single ion or molecule or virus compared to a monolayer, which are thousands of ions or molecules or viruses compared to my PhD research. So this is almost about 1,000 times more sensitive compared to the previous technology, just the plasmonic technology. And how it works is you bring a single ion. Again, you coat these nanoparticles with certain kind of chemicals which attract ions towards it, either because of pH changes or because of some kind of chemistry happening around it, because of there is more sulfur at the edge or more oxygen at the edge, which attracts the single ions that come and stick to the gold nanoparticle. Now, since the whispering gallery mode, which is light traveling around this sphere again and again because of total internal reflection, when you have these ions sticking to it, that light senses there is a slight change in refractive index, a slight change, the slightest of the slight changes in refractive index because of a single ion or a single molecule. But since light is traveling so many times, it amplifies the effect of the refractive index. And you can see this is the dip which I showed you. So this is the same dip here. And when a single ion comes and sit on a nanoparticle on the whispering gallery mode, there is a slight change in the wavelength at which this happens. The change is so small, you can see this is the whole range on the x-axis is 0.5 picometer, which is 500 femtometers. So this could be around tens of femtometers or 10 to 50 femtometers. It is very, very small compared to 100 to 200 nanometers, which I showed you in just the plasmonic based sensors. So this is a huge advancement in technology. And the coolest thing about this technology is Professor Frank Walmer, who I currently work with, has recently wrote a proposal to use this technology to detect the COVID virus. It's with the funding agency right now. They're looking at it, but the ion is few nanometers, whereas the COVID virus, as I've told you, is about 100 to 200 nanometers, which is almost 10 to 20 times bigger than ion. So if we can detect an ion, we should have no problem in detecting a single COVID virus. And we want to make it a reality and maybe take these devices and produce them in bulk. And then hopefully we can distribute them to UK-wide hospitals if possible, and if everything goes well according to the plan. By December is what we're targeting. Okay, so this is part of my postdoc research. Now there are very few more important applications of gold nanoparticles, which I wanted to talk about, even though I don't work on these topics, neither directly nor indirectly, but they're very important topics. And I thought it'll give you an insight into what more you can do with these gold nanoparticles. I'm almost at the end of my presentation, so don't feel sleepy or tired yet. Hang in there. So another important topic is cell imaging and tracking. This is another important technology which scientists and doctors are currently using. What they do in this technology is they put gold nanoparticles into cells, any kind of cell, and then they inject them into, for example, here they show a mouse, a rat. They inject these cells into a human rat, and these cells, they go around in the rat body, and if you do a CT scan, you can image where these gold nanoparticles are, and then you can image them over days and track the cells which you injected into the rat, where they're going, in which direction they're traveling. Are they concentrated in a particular part of the rat body, like rat's liver or rat's lung or rat's heart? This is a real-time image of a real rat body. They injected gold nanoparticles, and when you do CT scan, the rest of the rat body looks in a gray scale, but since you have nanoparticles inside the cell, you can clearly track where these cells are. So this is on day one when they injected the cells with nanoparticles into a rat body. They are mostly concentrated on the top half of the rat, and if you image them after a week, you can see them nicely dispersed around the rat. Well, you cannot see, well, you can actually see a little of the bottom of the rat, but there are not many in there, and you don't even know some of the nanoparticles might have come out in the rat's feces too. But yeah, this is one of the important applications for nanoparticles in cell imaging and tracking of cells. Another important application is targeted drug delivery. What you want to do, so there is a requirement in the biomedical field that when you take a certain drug, the drug might not exactly go to the part of the body you want it to go to. So you use nanotechnology to take this drug to the exact part which you want it to take to. And for example, here they show you here, they take hollow core nanoparticles, which is you have a nanoparticle shell, inside it is hollow. So you can put some chemicals inside this nano shell and send these nanoparticles into a human body. And then you can coat these nanoparticles with a certain kind of chemical. By that, what I mean is you coat the nanoparticle with a certain chemical, and this chemical might probably have a very high affinity or would like to go and stick to, let's say, human liver cells or a heart cell or a lung cell. And you inject these nanoparticles into the human body. And since the chemical you coated it would want to go and settle down near liver or heart, they go to the cells where you want them to go. And once they get there, you hit it with a light. And an important optical property which we learned about nanoparticles is when you hit them with light, apart from emitting out the electromagnetic field, they also lose a lot of energy via heat dissipation, which means they absorb and generate a lot of heat. So they heat up. And when you heat up these nanoparticles, they break down into gold components, gold molecules or gold ions. And whatever is inside these gold nanoparticles will be delivered to the exact cells where you want them to deliver. And here is again a real-time application where they show they injected uh, a certain kind of drug inside gold nanoparticles into a tumor cell, and this was inside a rat, and they send it into a rat, and then they hit it with the image first, and then they hit it with light, and then they image again to see how the tumor cell looks like after they delivered the drug and if it actually worked or not. And the final application I wanted to discuss was gold nanoparticles in cancer treatment. This is again a very important application, which is also currently in use by doctors around the world. So what you can do is again simple, just send gold nanoparticles coated with certain kind of chemicals which have very high affinity or would like to go and join the tumor cells because of whatever chemical you put these nanoparticles in. And when they go and sit with these tumor cells, you hit with light, and when you hit with the light, these gold nanoparticles absorb a lot of light, and then they start generating a lot of heat. Because of this heat from the nanoparticles, the cells around them, which are the tumor cells, they die because of this heat, and eventually you slowly kill the tumor cells around these gold nanoparticles. It's not a 1 day process. You usually have to do it over 2 to 3 months. The doctors usually they would do one session every week or one session every month over 2 to 3 months period. And this is also called as a radiation therapy, one kind of radiation therapy where you use nanoparticles and radiate with light and then kill the tumor cells. And I would like to thank all of the people who helped me conduct both my PhD research and also my current postdoc research. Dr. Syed Sadeghi was my PhD advisor. Dr. Yongbin Lin was a research associate at UAH who taught me and helped me how to make the nanoparticles on the cover slip, which I discussed. And Dr. Waylin Wing was a graduate student or a PhD student who was there before me. So he was a senior to me. So a lot of the experiments and how to build the optical setups and how to conduct experiments and how to write papers, I learned a lot from him. And Christina Sharp, she was a master and an undergraduate student while I was working in the lab. And Professor Frank Walmer is obviously my current employer and my current advisor too. And Dr. Ali Ataf, rather I'd say Professor Ali Ataf is a professor in Nipissing University in Canada. He helped us with a lot of simulations because research is not always about conducting experiments. You need simulations to actually understand what is going on and to prove the results which you have are actually the current results, and the theory which you come up is the correct theory by supporting your experimental results always with some simulations. And he provided us with all the important simulations which we needed to understand what was going on with our experiments. And any questions?
Yes, sir. We have just opened the chat box for the users for the participants to ask the questions. One of the questions that we have got is, are gold nanoparticles very expensive to use? Because we have mentioned the applications like in diagnosis and treatment of various diseases. So what about the cost involved for treating those diseases?
Well, obviously, the gold itself is just as expensive as the gold you buy for jewelry. The important part is the technology you need for using these gold nanoparticles and its applications. When you want a laser to activate these gold nanoparticles, or when you need all of those CT scan and other technology, they are quite expensive. And yeah, that's the issue. That might be another reason why this gold nanoparticle technology is not as widely researched in India, because the equipment which you need is quite expensive. Yeah, and only few rich countries in the world can afford to do that. Yeah. Okay, it's true. Yeah, it is true. It is quite expensive to do more research or use all of these applications in real life. Yeah.
Okay. One more question that we have is it possible now for common people to have gold particles in their diet?
Oh, well, Yes, absolutely. In some of the medicines which you might take might actually contain gold nanoparticles. They're so small, they don't actually affect your body a lot or interact your body a lot unless you are standing in front of a near infrared light source, a very high near infrared light source. So I would say yes, gold nanoparticles are included in a lot of supplements which we take, not maybe in a regular diet like food and fruits or beverages, but yeah, sure, in some medicines and supplements which we take.
Okay.
Oh, another important thing is you use these gold nanoparticles in your sunscreen too.
Okay, sir. Interesting.
Yeah,
Yes. So one more participant has asked whether it is toxic to humans because we say that it could be included in our diet.
yeah.
Is it toxic actually to humans? Can we consume that as such?
So why gold is so expensive, I think, is because it's so inert and it doesn't get bad over time, like rusting or anything like that, like how aluminum or steel or silver gets. And it is also very non-reactive with other metals. That's the reason why I think gold is being heavily used in these bio experiments, whereas you don't see a lot of experiments where they use silver or aluminum in these experiments, because it is quite toxic if you're consuming a lot of silver or a lot of aluminum or a lot of platinum, because they might change their properties after some times, and then they might react with your body in a different way than how gold reacts with your body. So I'd say it is perfectly okay if you consume gold in the right amount. By that, I what I mean is if it is less than few millimolar in concentration, I think it's fine, unless you're eating a kg of gold just by sitting there. Yeah.
Okay, sir. Yeah, thank you. The next question: can gold be used in allopathy?
I don't exactly know what allopathy is.
Like we have traditional treatments, no, sir. We have homeopathy and all such.
Yeah,
So,
I don't
yes, sir, you
know.
can proceed.
Uh, I seriously don't know. Maybe in the sense of drug delivery or something like that. But most of the gold nanotechnology in the current scenario needs needs you to do something more than just taking the medicine. And I don't know if allopathy does something like that. Allopathy or homeopathy usually just give you medicines or something like that. If I'm not wrong, that's what I know about homeopathy. But
Okay.
the gold nanotechnology, you need to do something more after that. After consuming gold, you need to hit yourself with some light source for it to do the amazing things it does.
Okay, sir. The next question, sir. How to check the antimicrobial activity of gold nanoparticles?
Antimicrobial activity of gold nanoparticles. So it's the same thing. So there is the slide which I talked about where you do cell imaging and tracking. The same thing happens. You take bacteria and you put it inside a cell or a tissue where you have the effects of this bacteria, and then you inside gold nanoparticles into this cell, and then you can image it as the bacteria grows, or if it is killing the cell, you can image it from inside what's happening, if the cytoplasm inside or the ribosomes inside or the protein inside the cell, how they are behaving by tracking and imaging the cell. That's one thing I could think of when you want to track or see the antimicrobial activity using gold nanoparticles. You might also be able to make these gold nanoparticles go and stick to bacteria and then heat these gold nanoparticles, but that will also kill the cell or the tissues
Okay.
along with the bacteria. So yeah, that may not be as beneficial, but yeah, I don't know. I haven't done research or looked into this topic as much, but yeah, there might be some yeah, very fascinating research that might be being done currently to to track these antimicrobial activities using these gold nanoparticles.
Okay, sir. The next question we have is how to easily find gold contamination in jewelry shops. Whether any simple methods are there that a layman can find that?
Well, I haven't worked in jewelry shop, or neither did I worked on jewelries. But the important thing is the gold which you use in these biosensing or detection or imaging experiments is 99.99% pure. So you can call it as 24 karat gold. But the gold which you use in jewelry or in utensils is not that pure, because pure gold actually bends quite easily.
Yes,
It
true.
bends like a plastic. So they actually dilute it with certain amounts of other metals to make it strong enough so that your jewelry lasts longer and doesn't break half.
Okay.
So I don't know how you can measure if there are other contaminants in there with it. But
Okay,
yeah.
sir. Interesting answer. The next question that we have is, when we crush the material into nano size, its strength usually increases. So, in that case, will it be harmful to our skin?
No, that's what I told. Like you use these in sunscreens, but these nanoparticles are so small, they can actually get into the top layer of your skin. And then when you wash it, it washes off. That's it. It doesn't do anything more.
Okay.
And your skin is also a little spongy, which means it is little elastic. So even if you hit your hand against a wall, not as hard as you're breaking your bone, but if you rub it against your wall, you don't feel them enough because these are so small. They just probably just go a little more into your skin and then just pop up back. That's it.
Okay. Thank you, sir. The next question. How do we measure the size of some gold nanoparticles?
So there is technology for it. It's a separate technology. I'd like to show an image for it. Okay. This image doesn't show it. Okay, let's see this image here. You all can, I hope you all can see the image.
Yes, sir. It is
So
visible.
this is each individual nanoparticle, and how we could image this is using an SCM machine. Some of you might know it, but some of you might not know it. So I'll tell you how this SCM machine works. SCM is scanning electron microscopy. So what happens is you hit any sample with electrons, and the electrons scatter back, and you have devices around in this machine uh, which absorbs these scattered electrons, and then there is a computer or a software which plots an image of how your sample looks like at the nanoscale. So each of these nanoparticle area here is 200 by 100 nanometer, and I could put a scale onto it, or I could tell how big it is, because usually these SCM machines are also scaled. So you usually take a small nanoparticle which you already know the size of. There are various nanoparticles of which you already know the size of. One of them is Air Force micro target, Air Force target 51, which has a glass slide, and on top of it you have letters. Actually, not letters. On top of it you have bars, and these bars are reducing in size as you go from one end of this target to another end of this target. They use this target in Air Force technology so that you can point laser as precisely as possible and something like that. But you know the size of each of this bar on this target precisely up to nanometers. So what you do is you put this target inside an SCM or some other imaging machine, and you draw a scale. Like you draw a line and see, okay, so the line which you draw on the screen is 100 microns, and then you take the sample out, put another sample, and then you draw another line on, like another line on this nanoparticle, and then compare the ratio of the line which you draw when there was an Air Force target and the line which you draw when you have a nanoparticle sample. And then when you do the ratio, you know the size of the nanoparticle. That's one way to do it. There are other ways. There is another technology called atomic force microscopy. What it does is it has a sharp pointed pin, and it has very few yeah, it has a sharp pin, and what happens is this pin literally runs on your sample, and wherever there is a bump, the pin pops up. Thereby you can calculate how tall your nanoparticles are. When I say tall, how high the nanoparticles are and how broad the nanoparticles are and all of that. But yeah, there are few technologies to do that.
Okay. Sir, can we take a few more questions?
Yes, yeah, I have
Yeah.
plenty of time.
Yeah, okay, sir. The next question. Is it feasible to deposit gold nanoparticles onto our human bones to get strength instead of titanium, like for ortho-related problems?
Mhm.
We usually use titanium. They're asking whether it is possible to deposit gold nanoparticles instead of using titanium for that.
um, I, I never heard anything like that, but I don't know. Maybe there is a reason why they don't use gold instead of titanium. Maybe it's because of you need to mix impurities into gold to make it a little stronger than titanium. I really don't know. I haven't seen or heard anything related to this.
Okay, sir.
Yeah,
The next
but
question.
it's a good question though. Yeah,
Yes, sir,
never thought
definitely.
about it. Yeah.
Yeah, okay. The next one. When we use gold nanoparticles over silicon substrates under high temperature in imaging processes, is there any interaction with materials?
Can you please repeat the question
Yes, sir,
again?
definitely. When we use gold nanoparticles over silicon substrate under high temperature in imaging process, is there any interaction with materials?
Yes, obviously. So when you say high temperatures, if you are increasing the temperature to about, let's say, 1,000 degrees Celsius, the gold itself evaporates. So the gold melts, and usually when gold evaporates, um, it goes down. So the gold nanoparticles might not be nanoparticles anymore. They might be just a thin layer of gold, because all of the gold melts and they just get together and it becomes a thin sheet, I guess. That's one thing. And also, if you go to high temperatures, again, 1,000 C, you also have a little silica deformation. So there might be some reactions between silica and gold. So I know there is another explanation. There is a better way of doing explaining this. When we talk about these uh, nanoparticle arrays on silica substrates, there is definitely the interaction between the nanoparticles and the silica itself. But how we exclude it in these absorption measurements is by taking a background measurement on just the silica substrate. And then we move the light to the part of the sample where you have nanoparticles on the silica substrate. Thereby, you take out if there are any absorption or any optical properties which happen because of the silica substrates itself. But
Yes, sir.
yeah, also we use silica substrates because they are quite stable until certain temperatures, but eventually at certain temperature every material melts. So it depends on what temperatures you want to work in. If you're working within 1,000 degrees Celsius, I would say there is very less material interaction. But if you're going over 1,000, your silica also starts deforming, and then it mixes up with your gold. So there are a lot of material changes in there.
Okay, sir. The next question. How can we synthesize gold nanoparticles?
Okay, so I've shown you how I synthesize gold nanoparticles in a solid base. This is how you synthesize gold nanoparticles, ranging from about 100, and you can go as low as 50 nanometers or even 20 nanometers. But if you want to synthesize gold nanoparticles to be put in gold solution like this, there are various chemical synthesis. What they do is they use a gold mixed with another chemical. To be frank, I don't know what chemicals they use, but what they do is they mix a gold solution which is mixed with another chemical with an acid or a base. I'm not sure, and then they rotate them at very high speeds, and then these gold molecules actually dissolve into small nanoparticles. And depending on the concentration of the acid and also the concentration of the gold chemical which you use, the size of the nanoparticles which you form, which they create, change. Is that clear?
Okay, sir. The
I
next
hope
one.
that's clear. Yeah.
Yes, sir, definitely. The next question. It was said that gold nanoparticles, it sticks onto the skin layer and while washing it goes off.
Yes.
But when it sticks means when sunlight falls on it, it will generate heat. Then how can we say that it is harmless to us?
Yes. Okay. So again, the various kinds of nanoparticles which you make have different absorption properties, right? And different emission properties, which is the scattered light. The nanoparticles which they use in sunscreen, they absorb the UV light, they reflect the UV light. That's how they do it. They don't absorb the UV
Yes.
light.
Okay, that
Does
is.
it make sense? So the sunscreen which you use is actually to reflect back the UV light. The visible light is still going onto your skin. Your skin absorbs the visible light, and the near infrared light, some of it will actually get into your body, some of it might even show up behind you. But the reason we use sunscreen is so that your body is not absorbing UV light, because if your skin absorbs UV light, it generates a lot of heat. That's why you have skin conditions like skin cancer or even tanning.
Okay.
You use gold nanoparticles so that you reflect this UV light.
Okay, sir. Interesting. The next one. How to link enzymes to nanoparticles?
Okay, so what happens is usually you take these nanoparticles and you coat them with various chemicals. There is one chemical called CTAB. Again, I don't know what the expansion of CTAB is. It has a big chemistry name to it. And usually a lot of these chemicals have uh, hydrogen ends or sulfur ends or oxygen ends. And lot of enzymes or proteins, they usually have higher affinity, or they want to stick to these hydrogen or sulfur or oxygen molecules. That's how when you have a gold coated with any of the material which has a end molecule as hydrogen or sulfur or oxygen, they attract these proteins or enzymes and then they stick to the gold nanoparticle. It's as simple as that in explaining, but if you want to do it, actually it is not as simple as that. It has a lot more complications to it, whereas you have to keep the temperature consistent and you have to mix them at a certain speed and you have to use the right concentration of the chemicals. Yeah, that's how you do it though.
Okay, sir. The next one. How to synthesize non-spherical gold nanoparticles?
So non-spherical gold nanoparticles. This is interesting again. So this has nothing to do with just the fabrication of the nanoparticles itself, but it has more to do with the chemistry of it. Some of the chemical molecules, when they form, when you look at the structure, like, let me explain. If you have a benzene, I'm just explaining this as an example. This is not a real-time example, but if you look at a benzene molecule, it is usually a closed structure. You have like a hexagon structure. If you look at the molecule itself in real time, the molecule also looks very similar to that. You have like the carbon-carbon bonds, which are all interlinked. There are other molecules which form in a shape of a star. That means there probably is a there probably is some chemical which you look at it in a microscope, it looks like a star. And what they do is they take this chemical, they attach some more chemicals at the end of it, and then they do the chemistry. So the gold forms at the ends of it. And then when the gold falls at the ends of it, they start to grow more gold on it. And eventually when the gold grows on top of this chemical, it looks in the shape of whatever the chemical inside it is. So it could be a star, it could be a ring, it could be a shell with chemical inside or a drug inside too. Or you can make rods. There are so many amazing shapes. Uh, you cannot even imagine of, well, I cannot even imagine of so many complicated shapes, which a lot of chemists usually make. But yeah, that's how they do. It all depends on the chemical molecule you use, and then the chemistry surrounds it, and then you start building gold around these molecules, and then you grow more gold on it, and then eventually you have whatever shape of gold nanoparticle you want.
Okay. The last question, sir. How do we calculate the number of antibody molecules bound to gold nanoparticles?
Okay, so number of antibody molecules. Let me just go back to the slide where we were talking about this. Okay, so this is a slide where you can either detect, or this is a technique where you can either detect ions or antibodies or viruses or any chemical you want. So what we do in our experiments is we dilute these molecules so much that there are probably just few hundreds of any molecule in a given solution. Okay, and then what we do is we track these peaks. When you track this peak, what I mean when you track this peak is we have a MATLAB code, and what this MATLAB code does is it finds the peak point, and then it starts tracking this peak point, how it moves over time. And then if there are no molecules or antibodies or ions around the gold, the track or the trace of this peak looks flat. But whenever there is even a single antibody or ion which comes and stick to this gold nanorod around this resonator, we see a step or a bump, because the wavelength is not the same anymore. The trace doesn't look flat anymore. You see a sharp step. And then depending on how many steps you see, you can just count how many antibodies or how many ions or how many proteins you have.
Okay, sir.
I hope that was clear. If you want more explanation, sure, I can show you some more images I have. Yeah.
Okay. Thank you very much, sir. You've patiently taken up all our questions.
Yeah, no problem. Thank you. Oh, I thought my screen was sharing. I'm sorry. Is my screen
No, no.
still
Yeah, yeah.
sharing?
Yes, sir. Your
Okay,
screen is
all
still
right.
sharing.
Yeah. Okay, yeah. Are there any other questions? Or um, I'm sorry I did not include my email ID on the first slide, but yeah, if you have any questions, Padma Priya madam has my contact information, and Praveen sir also has my contact information. You can either contact one of them and then get in touch with me later if you have more questions, or if you're interested in similar kind of research, or even this research and would like to read more about it.
Sure, Ritvik, we will share
Yeah,
it with the participants if they need it.
yeah, yes, ma'am. Thank you.
Yes, sir. Okay.
Oh, finally, I wanted to tell this. Hopefully, you all are safe and healthy, and yeah, try to be in a safe place. And follow the lockdown restrictions and everything else that is being kept in place in India right now, and try to help each other, your families and friends, and see if anyone needs any help with a lot of things. You probably heard a lot of things happening in India since the lockdown started. So try to check on your friends as regularly as possible. Not all of them might be as fortunate as you are. So just check on them and make sure everyone is happy and fine uh, in these months. Okay. Yeah.
Yes, sir. Thank you very much.
Yeah. Thank you, ma'am.
I thank all the participants who are present with us today. And hope you would have enjoyed the session. And yes, most of our questions have been answered by our resource person, Dr. Ritvik. We have the upcoming webinars for tomorrow. Tomorrow, there are two webinars that are scheduled. One is How to Become an Entrepreneur by Mr. Prashant Rajan. This is part of our alumni series scheduled between morning, it is actually 10 to 11. And the next webinar is on the same date is tomorrow. It is on Electronics Revolution in Scientific World by Dr. Karupannan, MNNIT Allahabad between 2 and 4. I request all faculties and students to attend the webinars and get benefited. Let's meet tomorrow. The certificate link will be posted in our chat box. I request the participants to fill it. And yes, thank you.
Thank you, ma'am. Is it? Yeah. Is it okay if I end this?
Yes, sir.